Good evening to all. So, welcome to today's interactive session. This is for week 9. I'm one of the TAs for the course Foundation Engineering conducted by NPTEL. Our course instructor is Professor Kousik Deb. So, my fellow TA is Mr. Shivshankar Nandi. And so, this in this session, we'll be focusing on the content that was discussed in the previous week, week 9. Uh, in this week we dealt with earth pressures. So the earth pressure is nothing but the pressure exerted by the soil on any structure. So generally we are interested in finding it because of we are in many cases we'll have to design retaining walls, dams, and footings. So in all these cases, the sheet piles. In all these cases, the structure is experiencing a pressure by our soil. So there are different ways to calculate. So we'll be looking at it. So in the last week, just to fresh up, our course instructor, he discussed many things. So it was started. We started with okay. We started with earth pressure. When I say earth pressure, it's a general term. So here we are interested in lateral earth pressure. Lateral earth pressure means the earth pressure which is acting laterally towards our structure. So when we say lateral earth pressure exerted by our soil, there are three different conditions, that is active state, passive state, and earth pressure rest. This is when the retaining wall or any plane, if we are if it is moving away from our backfill. So uh, when our structure is moving away from backfill, the soil exerts a certain pressure on the retaining wall or the structure. This is called passive earth pressure. And sorry, active earth pressure. Passive earth pressure is when the irritating wall is moving towards the backfill for whatever reason it might be. So towards the backfill. These two earth pressures are different. Passive earth pressure is greater than active earth pressure, and here we have the earth pressure depends on the different properties of the soil. And here there is one when the retaining wall is not moving at all, or if there is no retaining wall also, we can calculate the earth pressure at any depth we need. That is called earth pressure at rest. So there is no movement of the wall. So in all the three cases, we have different earth pressure coefficients, that is Ka, Kp, and K0 respectively. So these earth pressure coefficients are functions of, for in a simplistic analysis, it's a function of phi. Uh, so this is for cohesionless soil. Now, um, Rankine has come up with a theory that is for calculating the earth pressure. So, in the basic assumptions, it was assumed that the backfill is horizontal and it is cohesionless soil, and it's not homogeneous. There is no surcharge. So all these things, the back of the wall is vertical. So all these things are assumed, and Rankine came up with the earth pressure theory. So in the last week we discussed about different cases in the cohesionless soil when there is no surcharge and when there is uniform surcharge above the backfill, and when the backfill is submerged, so that is the presence of water table is there. And when there is a backfill is sloped, if there is an inclination of the slope behind the backfill, and when the backfill is layered. So all the exceptional cases were also discussed. And though this is only applicable for cohesionless soil, the the theory was also extended to deal cohesive soils also, that is C5 soil. When it comes to C5 soil, a new thing also comes into picture, that is our tension crack. So what happens is, if cohesion is coming, we have the soil gets an ability to stand without any support vertically. So that depth is called tension crack. Sorry, that depth is called critical depth. And if we due to this cohesion, the tension stress is developed, and due to this, there is a tendency of crack due to this during our active state. So this crack is called tension crack, and that is also discussed. So and towards the end of the week, sir also solved a lot of problems of different cases. So today we will solve a few problems, and let us see how it goes. So in the first question, I have chosen a problem with our backfill when the backfill is inclined. So when the backfill is inclined of 20 degrees, so we have a retaining wall of 10-meter high, and cohesionless soil we have in the backfill, and the surface of the backfill is inclined with the horizontal. So the unit weight of the backfill is given, angle of internal friction is also given. We are supposed to find the horizontal component of the total active thrust. So the total active thrust is actually inclined a little bit at the same angle as the angle of inclination. So if it is like this, and if we have a retaining wall, we have if this is the angle I, the same angle I, there will be a lateral earth pressure. So this PA will be also inclined to the horizontal by the angle I. So what is this PA? To find this PA, we need our lateral earth pressure coefficient. So lateral earth pressure coefficient for an inclined backfill in the active case is given as cos I, where I is the angle of inclination of the backfill, into cos I minus root of cos square I minus cos square phi divided by cos I plus root of cos square I minus cos square phi. So with this formula, we can find the coefficient of lateral earth pressure. So once we have the coefficient of lateral pressure, it's quite easy to find our total active thrust. So let us go for it. So we have this thing. So just let me just write all the values. I is equal to 20 degree. So this I is also 20 degree, and if I'm expecting a backfill, the total active thrust, this angle is also 20 degree, and this can be written as half into gamma, sorry, half into Ka gamma h square, where this is the h we have, and h is equal to 10 meter in our case. So 10 meter, and this height is also h by 3, but here it is not asked, so this will be 10 by 3, whatever. So this particular pressure at the bottom, it will be small pa, that will be Ka as usual, Ka gamma h. Okay, so what is Ka here? Let us find Ka. Ka is equal to cos 20 into cos 20 minus root of cos square 20 plus cos square 30, because our phi value is 30, and divided by cos 20 plus root of cos square 20, sorry, this is minus, so 20 minus cos square 30, cos square 20 minus cos square 30. Okay, so this turns out to be 0.414. So the lateral earth the coefficient of lateral earth pressure, active lateral earth pressure is 0.414. So now we can directly find out our PA. So the capital P, I am directly finding the total active thrust. So that is half into gamma Ka h square. So this is half into 18 into 0.414 into 10 square. This turns out to be 372.78 kilonewton. But in the question we are asked to find the horizontal component. So when we have this as the total earth pressure, so this is 372.78 kilonewton, and I need horizontal. So if I'm resolving this horizontally, I can directly find it as cos I, right? So this will be PA cos I. So I can write horizontal component is PA cos I, sorry, excuse me. This is 372.78 cos 20. That turns out to be 350.30 kilometer. So that is one of the options we have, 350 kilometer. So that's how it is done. So here in the initial Rankine's theory, this was supposed to be a horizontal backfill, but it was extended by taking the element as inclined element, and we arrive at this lateral air pressure coefficient. Okay, so that is, here we have to remember that the inclination of this base is also I. So our load will be parallel to the backfill. Okay. So now let's solve a bigger question. Here we have a, retaining wall, 12 meter long retaining wall, two layer. So we have a layered soil now. So Rankine started with a homogeneous soil, but it was later we can extend it to a layered soil, and properties are there as in the given table. Okay, the water table is at a depth of 4 meter from the ground surface. Find the total lateral earth pressure. So here we are supposed to find this lateral force and locate the point as well as the magnitude of this lateral force uh, if the active earth pressure is in action. So we in the active state we are supposed to do it. So we know the different layers of the soil, both are cohesionless soil, and so let us assume this is the how it looks like. So here we have the water table. So here let this be the groundwater table, and we have this as 12 meter, and here this is 0 meter, and at 4 meter we have water table, at 8 meter we have the next layer, and till 14 meter. So we need not go till 14 meter. Now let us see what is the density here. The density here is 19, sorry, 17, the dry unit weight 17 kilonewton per meter cube. In the layer 1 itself we have saturated as 19 kilonewton per meter cube, and in both the cases phi is equal to 35 degree. Here gamma sat is 20 kilonewton per meter cube, and phi value is 40 degree. So that's how it is. This is the whole thing is layer 1, and this is layer 2. Now we can find Ka1 and Ka2. So for layer 1 let it be Ka1. So for active condition we know that Ka1 is equal to 1 minus sin phi by 1 plus sin phi. So I can write Ka1 is equal to 1 minus sin 35 by 1 plus sin 35. that will be 0.271. Ka2 will be 1 minus sine 40 by 1 plus sine 40. This will be 0.217. Okay. So we know both the lateral earth pressure coefficients. Now, let me write it here. So here Ka1 is equal to 0.271, Ka2 is equal to 0.217. So in a way we can judge something. For example, here since phi 1 is less than phi 2, our Ka1 is greater than Ka2. So it's the other way, right? So what it means is, like, if we have the lateral earth pressure of the top layer will be in a smaller rate, or in a larger rate it will increase. But since the bottom layer is stronger, the lateral earth pressure will be lesser. So stronger the material, it will exert lesser lateral earth pressure, right? For example, we have a rock. It can withstand. So it is so strong that it can withstand. It will not apply any lateral earth pressure. So it can stand vertically. But if it is water, water has the least thing. So there we cannot. The lateral earth pressure won't. Whatever it will be. It will exert whatever it vertical pressure. The completely will be exerted horizontal. That is the Pascal's law. That is nothing but Ka1 is equal to 1. So Ka for water will be equal to 1. So that's since it doesn't have any shear strength. So the stronger the material, the Ka1 will be the lesser. That's the idea what I wanted to say. So that's why we could see if we figure out how much the lateral pressure that we are going to find out. That's why we will find that in the stronger layer, sorry, in the stronger layer, the earth pressure will not be that much as compared to the weaker layer. So let us see. What we have to do is, we will have to logically we can find out the shape of this profile. So that's what I wanted to point out. So here from the top layer, we know it's linear till the water table. Below the water table, we know we have to take uh, consideration of the this water table. So below we will have to take submerged unit weight when we are considering lateral effective earth pressure, and we have to add this hydrostatic pressure. So it will increase, and at the interface of these two layers, that is this at 8 meter, it will shift to a lower value, because that's the point I wanted to highlight. Because our Ka2 is smaller, so this will shift back. So this point will shift back here, and then it will again linear till our base point. So we can calculate and see how the numbers are. So let us find this pressures at different depths, and so that we can find the whole area of this profile. So what let us see what is the pressure at 4 meter depth. So at 4 meter depth, let me write it as PA1. So if I want to find PA1, it's straightforward. We have 4 meter depth, so I can multiply 17 into. Okay, so let me write just for clarity: gamma Ka gamma H. It's as simple. So here it will be Ka1, and I can write H1. So let me write it as okay, gamma 1 also. So 2.271 into 17 into 4. It's as simple as that. So the value turns out to be 18.43 kPa. So it's 18.43 kPa at this depth. That's clear. Now, what is the depth what is the pressure at 8 meters? So as we are moving down, we'll use the same Ka1 value and arrive at a value that is, let me write Pa2. This can be written as Ka1 gamma 1 H1. That is the contribution from the first 4 meter plus. Okay, so here let me write this as H1, H2, and H3. All are for 4 meters. So the second layer, that is below the water, it will be Ka1 gamma 1 dash. That will be the submerged unit weight, and H2 plus this is since this is submerged, I'll have to add my hydrostatic pressure also. So that will turn out to be gamma W H2. So this value, the first value is nothing but what we had found before. So I can write it as 18.43 plus the second value will be Ka1, so 0.271 plus sorry, into gamma 1 dash. Gamma 1 dash is nothing but 19 minus 9.81. That is my saturated minus unit this density of water into 4 meter plus my hydrostatic pressure, that is 9.81 into 4. So that will be 67.63, isn't it? Sure, let me just cross check. So 18.43 plus 8.27. Okay, so that's P. So 67.63. So 67.63 will be my pressure at 8 meter. But after the interface is crossed, uh, I have a different at left pressure coefficient. For in that case, I'll have to find one more pressure at the same depth using my Ka2. So that will be Pa2. Let me write dash. Pa2 dash will be my Ka2 gamma 1 H1. So this is the contribution from the first top layer plus Ka2 gamma, sorry, gamma dash, gamma 1 dash, that is a soil below the water table, into H2 plus gamma W H2. So this will be 0.217 into 17 into 4 plus 0.217 into 19 minus 9.81 into 4 plus 9.81 into 4. This turns out to be 61.97. So you can see that it's slightly lesser than our previous value. So my this pressure will be 61.97. So that's that. So at the last one also we can find, that is PA3. This will be the base. So I have at 12 meter depth. So I have different same. So Ka2 gamma 1 H1 plus Ka2 gamma 1 dash H2 plus Ka2 gamma 2 dash H3 plus gamma W H2 plus H3. So in this case hydrostatic pressure is there, hydrostatic pressure is there for both the layers, that is for not both the layers, partially for the first layer and completely for the second layer. So I'm writing H1 plus H2. Okay, so in that case we have I can substitute the same thing. So here I have 0.217 into gamma 1 is 17 into 4 plus 0.217 into 19 minus 9.81 into 4 plus 0.217 into my second layer is 20. So 9, so the submerged will be 20 minus 9.81 into 4 plus 9.81 into 4 plus 4. So that is a both the whole thing below water table. So this will be 110.06 kPa. So I can write it here as 110.06 kPa. So that's the idea. So I hope you understand why this is moving back here, because our K1 and K2 are different. So in at each layer interface, we are supposed to be careful in that thing, whether it is moving. Sometimes the bottom layer might be weaker. In that case, our K2 value might be higher. So in that case, it will this point will shift forward at the interface. So okay, so that's it. So let me just write the values here. So here the idea is we have to find the area, the whole area of this, the whole area which is by covered by this pressure distribution. So to find it, you can either divide it into different trapeziums. So we have three trapeziums, right? That is for these three different trapeziums we can find the area. So if you know the formula for to find the area of a trapezium, you can do that. And at the say, or we can also, but when we are doing trapezium, we need to find the centroid also. That is also a challenge, but there is a formula for that. So we have to find the area of one triangle and two trapeziums. So we have one triangle and two trapeziums. So uh, then we can have to find the centroid of area, or we can divide it into different sets of rectangles and triangles. So just like this. So I can divide that into different triangles. So let me just write the values here so that I can find the area. So we have 18.43, 18.43 kPa, 67.63 kPa, and 61.97. So this one is 61.97 kPa, and here I have 110.06 kPa. Okay, so I have these sets of triangles and rectangles. So I can easily find the centroid of these figures. So let me name it like P1, P2, P3, P4. So let me divide these forces as P1, P2, P3, P4, and P5. Assuming that this is figure 1, 2, 3, 4, and 5. Okay, so let me see. So my first force, I can write it as uh, I'll write P1. P1 is equal to half into base into height, right? So base is 18.43 into height. This is 4 meters. So each one is 4 meter. So this is actually 36.86 kilometer. And P2 is equal to this rectangle. This rectangle's width is 18.43, but height is 4. So we can directly find it as into 4. This is uh, 73.72 kilometer, and P3 is equal to this triangle. So in this triangle we have height as 4 meter, but the base will be 67 minus 18. So half into base is 67.63 minus 18.43 into height. So this will be 98.4 kilometer, and P4 is equal to the rectangle. So the size of the rectangle here is 61.97. So this width is 61.97. So 61.97 into 4, this is 247.89 kilometer, and P5 is equal to the area of the triangle. So half into base is nothing but 110.06 minus 61.97, so into 4. So this value is 96.18. Now, if I add all these values, I can get my total lateral earth pressure thrust. So, my total lateral thrust is equal to P total is equal to P1 plus P2 plus P3 plus P4 plus P5. This is 36.86 plus 73.72 plus 98.4 plus 247.89 plus 96.18. This turns out to be 564, I guess. No, not 564. Let me check. So 36.86 plus 73.72 plus 98.4 plus 247.89 plus 96.18. So this is 553.36. So we have our total lateral thrust. Now we need to find uh, locate the point of application. So we have to understand that there is we have a force which is a total force. What will be the elevation of that force? So we need to, so there is we can take the weighted average of all these forces so that we can get one single average elevation. So let us find out the elevation for each force. So P1 is actually 4 plus 4 plus 4 by 3. So 4 plus 4 plus 4 by 3. I'm measuring it from the base. So 4 plus 4, because in the question we are supposed to locate the application of pressure. Okay, they have not uh, told anything, but we can say that from the base. So our final answer will be with respect to the base. So here I have y1 is with respect to base. So 4 plus 4 plus 4 by 3, since it's a triangle, the this thing will be 4 by 3. So this turns out to be 9.33 meter, and y2 will be for the rectangle second number 2. So here we have 4 plus 4 by 2, because this is 4 by 2, that is 4 plus 4 by 2, this is 6 meter. And triangle for the figure 3, y3 is equal to 4 plus 4 by 3, this is 5.33 meter. And for y4, so in convention, if you are getting confused, I'll rather write it as z1 z2 z3. So z1, because in many textbooks I think sir also used z values. So in order to avoid confusion, okay, z4 is equal to, it's a rectangle, so here it's just 4 by 2, so it is 4 by 2, that is 2 meter. And for the last figure, that is z5, we have the elevation as 4 by 3, so that will be 1.33. So in order to locate the height of uh, point of application from the base, this will be P1 Z1 plus P2 Z2 plus P3 Z3 plus P4 Z4 plus P5 Z5. This is nothing but the weighted average of all the elevation. So this will be P1 plus P2 plus P3 plus P4 plus P5, which is nothing but the P total, whatever you calculated. So this value I can, okay. So this value will be 36.86 into 9.33 plus 73.72 into 6 plus 98.4 into 5.33 plus 247.89 into 2 plus 96.18 into 1.3 divided by the total force. So my total force is nothing but 553.36. So this will be 3.497. Just to check. Okay. So this is my point of application. So what it means is that at 3.449, that is nothing but 3.5, that will be somewhere here. I have this. Okay, I will use this color. So at this particular level I have my P total, and this is almost 3.5 meter from the base. That is the idea, uh, or rather here. Yeah. Okay, so that is the idea. So we know the point of application. So why do we need these things? Why are we calculating this earth pressure is because when we are designing this particular lateral. So when we are if we know the if we want to uh, design this retaining wall, we need to know what is the pressure acting on it. So whatever the profile is, whatever complex the profile is, we want to know the total pressure loads acting, so that we can hypothesize it as a cantilever fixed, and so that there is some load here, and we can find the moment and shear force involved, moment, bending moment, and shear force involved can be found out, and using that we can find the concrete required and the steel required. So to design this, the structural design of retaining wall depends on we for that we need this data. So this bar, as well as if it is in below the soil, we'll have in this direction also, and also from the base, if you know the bearing, how it is, eccentricity and all, you can use to understand the how the pressures are. So using all these pressures, we are supposed to uh, design our retaining wall. So that's why we are doing these things. Next, now let's go to the next problem. So in this problem, we are dealing with passive earth pressure. So we have a retaining wall, 4 meter high. Backfill is C5 soil. So till now I was showing granular soil, cohesionless soil. In the previous session, interactive session, my fellow TA, Mr. Shivshankar, he solved a couple of questions using for C5 soil. So here also, but that was for active pressure, active case. So here I'm going to solve for passive case. So we have a horizontal backfill. We know the details about the soil. It has a surcharge also. So if the wall is pushed towards the backfill, that is pushing towards the backfill itself means that it is a passive case, and we are supposed to find the total passive pressure. So um, let us see. So here we can find the first right away we can find what it is, what the lateral earth pressure. So passive earth pressure coefficient is equal to Kp. Kp I can write as sine phi 1 plus sine phi by 1 minus sine phi. This is 1 plus sine 30 by 1 minus sine 30. This is nothing but 3. Okay, so that we have. So since we have that, we can directly start. So let this be the figure. So here uh, the retaining wall is moving towards the backfill. So we have a surcharge on the backfill. This surcharge is, let it be, Q is equal to it's given as 20 kPa. So our density is also 20 kilonewton per meter cube, and phi is equal to 30 degree, and our Kp is equal to 3. Okay. So first component. So this is the earth pressure figure profile. So first component, that is, let us say 1. So let us divide this by 3 figures. First component is contributed by the surcharge. So that will be our QKP. Okay. Second component is because of the cohesion. So because of cohesion, what happens is, in active case and passive case, we have two different cases. In active state, what happens to the profile is like, it is, the earth pressure is reduced by a value throughout the depth. So this value, I can write it as 2c root Ka. That is the idea. So in active case, the profile, so earlier without cohesion it used to be like this, and with cohesion the whole profile is shifted towards the left by active, during active case, by a value of 2 root 2 CKA, and that's why we will have a negative negative pressure at the top, negative stress at the top, so that causes our tension crack, and whatever this critical depth concept occurs. But in the passive case, it's the other way. So if this was the profile before considering cohesion, after considering cohesion, it changes to be this. It shifts. It adds to the it adds to the, what do we say? It adds to the lateral pressure, that is by a value of 2c root Kp. So this is the difference. So in this case, we will take the second box as 2c root Kp, and this is, as usual, we have Kp gamma h. In our particular problem, h is 4 meter, and so my P1, I can write P1 as QKP into H, that is 20 into 3 into 4, that will be 240 kPa kilonewton. Now I'm directly finding the force, that is P1, we have P2, and at the center we have P3, and P2 can be calculated as uh, 2c root Kp, this is the base, into height 4, that is h. So 2 into, what is my C value? C value is also 20 kilometer. I forgot to write it. C is 20 kPa. So 2 into 20 into root 3 into 4. This is 277 kilonewton. And P3. P3 is nothing but the area of the triangle. So half into Kp gamma h into h. Sorry. Kp gamma h into h. This is half into 3 into gamma is 20 into 4 into 4. This will be 480 kilometer. Here there is no water table involved, so we are directly taking the gamma value. If the soil is submerged, we are supposed to take submerged unit weight, because this Rankine's theory is applicable only for effective stresses. So this Kp and lateral earth pressure coefficients is a ratio of effective vertical stress by uh, horizontal vertical stress. Sorry, horizontal vertical stress by effective. So our K value is actually horizontal by vertical. So this is both are effective. That's why whenever we are using our lateral earth pressure coefficient, we are supposed to take effective stresses. So, but in this case, water table is not involved, so we can directly take this 20. So that's it. So let us find the total passive thrust P is equal to, I can add all these two, so 240 plus 277 plus 480, this is 997 kilometer. And what are these locations of these forces? So I can write Z1 is equal to 2 meter, that is 4 by 2. Z2 is equal to also 2 meter. Z3 is equal to 4 by 3, that is 1.33 meter. So my Z average, that Z effective is equal to 240 into 2 plus 480, 277 into 2 plus 480 into 1.3 divided by 997. So this is 1.677 meter. So I can say that somewhere here my total force acts, that is my PP, let's say 997 kilometer. Okay, so that's the passive case. In passive case, nothing much changes. We are just using the formula for our earth pressure changes, and this concept also we have to adopt when our cohesion is coming into picture. Okay, so uh, that is straightforward. Now let us solve few for just to make it wind up. Before we wind up, let us solve a few small problems. So here we have an MCQ problem. So here let us try to solve this. We have a retaining wall. So this retaining wall, we have a C5 soil, and backfill moves slightly away from the backfill. So it is moving slightly away from the backfill. So when I say away from the backfill, we know that is active case. So under this condition, Mohr circle for the state of stresses at the ground surface. So we are supposed to plot the Mohr circle under the ground surface. Then how would it look like? So we C is the cohesion, K is the, so let us just plot this thing in the Mohr circle and see what happens. So once we plot, I think we can arrive at which formula this is. So here let us just plot, uh, draw the thing. So here we have retaining wall, and this is an active case, so retaining wall is moving away from the backfill, and we have C5 soil. So as I told you, in active case we have the profile like this, where this particular value is 2c root Ka, and this particular value will be gamma Ka gamma h minus 2c root Ka. Basically throughout the profile 2c root Ka will be subtracted. So since before considering cohesion it was 0 at the top, we are subtracting, so it goes to the other direction. So this is actually negative direction. So this is acting like this, and this is acting towards the wall. That is the idea. So this is the profile. We have a C5 soil. Okay, so we are supposed to draw the Mohr circle for this. What will happen at the top? So if we have an element, just draw it properly. So if we have an element at the top, let us say here at z is equal to 0, what will be the normal sigma 1 and sigma 3, sigma 1 and sigma 3. So we know that in in active case, my vertical stress is sigma 1. So I'm just drawing this here. So in my element sigma 1 and sigma 3 I have. Sigma 1 is nothing but gamma z, that is 0. since z is equal to 0. Sigma 3 is nothing but at the top we have minus 2c root k. So with sigma 1 and sigma 3 we have. So how to plot that in my Mohr circle? So if my Mohr Coulomb surface, if I have, I can draw this as, so sigma 1. Okay, so wait, let me draw this straight. Okay, so this is better. So let us just assume that this is the Mohr Coulomb surface. So here, since we are dealing with negative stresses also, I have brought the axis to the middle. So here I have shear stresses, I have shear normal stress. So what happens is, one, my sigma 3 is at negative, so this is 2c root ka, and my sigma 1 is at 0. So if I draw a Mohr circle, I'll get it like this. So this is sigma 3 and sigma 1 is equal to 0. So that's how my Mohr circle would look like. So here, um, so let us see what are the options are. So one option is, A is point circle. So it's not point circle. We know that the diameter of the circle is diameter is 2c root ka, and origin is, sorry, sigma 1 is at origin. So let us see. So this is not the answer. The second option is circle of diameter, okay, passing through the origin and laying towards the positive axis. So it is not towards the positive axis. Here it is positive and here it is negative. So our Mohr circle is towards negative, right? So not the second option. Circle of diameter with its center at origin. The center is not at origin. Here the center is towards negative direction. A circle of diameter to root 2c root ka, passing through the origin and laying towards negative direction. So this must be our answer. Okay, so that's how it is. Okay, so we'll solve. So this is the um slide which was explained in the class. So in this particular question, we were dealing with this particular case, that is at z is equal to 0. So that's what this violet circle indicates. So another thing is, like, if there is an tension crack that is at this point, if we have PA is equal to 0, that's where our pressure is equal to 0. In that scenario, our this will be the orange Mohr circle. And on other cases, at a depth of z, at anywhere below this point, we will have this uh, blue circle. Okay. So having said that, let's do one more problem. Here we are supposed to find the failure surface of this rupture surface of the backfill made by this. So in this question, this is dealing with Rankine's theory, and the rupture surface. This is rupture surface, nothing but the failure surface of the backfill. What is the angle made by it with the horizontal? So under passive crustacean. So before that, I would like to uh, show this case. So in this plastic case of both the active and passive thing, let us say a soil is failing with respect to active and passive. It is said that it will have different slip lines. So if it is this, let us say this is active. This is a trick to remember this. So I'm trying to show a trick to remember what it is. So let us say this soil is failing in left side, it's active, it's failing in active case, and the right side is in passive case. For whatever reason, let it be bearing capacity, either footing is acting on it, whatever load is acting on it. Let us say that it is failing. So the slip lines will be like, in the active case, it will be like more of a steeper lines. it will like be like this. So diamond shape. So the lines will be steep. So I can project one line, and if I uh, take this angle, this will be 45 plus 5 by 2. So it is quite clear that this angle is greater than 45. That's why I mentioned it is steep case. This will be 45 plus 5 by 2. But in the case of passive case, it will be a less steeper. So it will look something like this. In this case, if I extend one line with the horizontal, this will be less than 45, so I can write it as 45 minus 48. So in the plastic state, this is how it works. So at the failure, this is the slip lines it would look like. In both the cases, uh, phi, it is dependent on the phi value. So in other words, it is also shown in this class in one of the slides. When it comes to retaining walls, this is what happens in the active case. As I told, the slip line will make an angle of 45 plus 5 by 2 with the horizontal, and in the passive case it will make an angle of 45 minus 5 by 2. So that's what I wanted to point. So if you are unable to remember this, this is something that you can remember, because in the passive case it's our k value is higher, so we are supposed to displace a bigger wedge. So in order to get a bigger wedge, we need a lesser angle here, that is 45 minus 5 by 2. So because why it is a bigger edge? So because our value is bigger, our our kp value is higher. That's why I can write kp is greater than ka. So this wedge which is involved is smaller in active case. So that's why this angle is 45 plus 5 by 2. That is also a way to remember. So if you remember either this particular concept or this concept, it's up to you. Okay, so that's how. So in this case, Rankine's theory of rupture in the case of passive with respect to horizontal. So passive with respect to horizontal is nothing but over 5 minus 45 minus 5 by 2. Okay. So in today's session, we discussed one problem on uh, inclined backfill, and one with C5 soil. One with layered soil, cohesionless soil, for with two different soil layers, and another one with C5 soil. So towards the end of the week, in the last week 9, there were a lot of problems solved by our instructor. Uh, for example, different cases with water table, without water table, and with different complex shapes. I would suggest you to go through all those problems so that you will be able to do any given soil profile or conditions. You'll be able to draw the profile. Once you the only idea is to you should be able to draw the profile, so that you will be able to judge how you should design the retaining wall. In this case, it could be sheet pile also, it could be a footing also. So for different cases, we need to understand the lateral earth pressure acting on our structure. So that's it for today. So if you have any doubts, please feel free to ask. Also, you can also post the doubts in our discussion forum. Nobody is posting any doubts, so but I would really suggest you to do that. That's how we can make it more worthwhile.
Hello, sir.
Yeah, yeah.
Uh, so your explanation and as well as Shubhu Shankar's explanation is excellently good, but I'm not getting time to solve it or go through the video lectures.
Okay.
Um, but I do have interest in learning completely foundation engineering. I
Okay.
don't know what to do. Assignments also I could not able to do day before yesterday.
Uh-huh.
Mm. And the previous since 2 3 weeks I'm not able to concentrate. And which forum have you sent the links out so that we can post any doubts on
Do
that?
you mean discussion forum?
Yes, sir.
So in the course page, there is a button called Ask a Question. So
Oh,
if you go there, there is a directly you will be sent to a Google forum, which is just made for this. So you can type it there.
okay.
We have two regular TAs, two TAs as part of this NPTEL, and sir will also respond if needed.
Okay. Can we get the recorded sessions, sir? When we miss the classes, no,
Yeah,
do
yeah, definitely. Like we are uploading it regularly. I hope you are getting those links. So the YouTube, we are uploading this particular session every
okay.
week. We are
Uh-huh.
uploading it in YouTube.
Okay.
You can also, if you are unable to access it, you can also post in this discussion forum that I'm talking about.
Okay.
Uh,
Okay.
uh,
Mhm.
so so that so it's actually in YouTube. Actually, if you search my name like Kashyap Vasudevan or Shiv Shankar Nandi, we have a
Mhm.
YouTube channel. We are posting it every week.
Okay. Uh-huh.
We are
Uh-huh.
told that the students are given the list of links also for this particular PPT as well as the videos link. So
Okay.
just
Mhm.
make sure you can access it any time. So the
Okay.
time management, it's you have the freedom. That's why we are
Oh,
posting it.
yes, sir. Sir, Kashyap sir, can I post through WhatsApp if you after this course ends?
Yeah,
If I get any doubt, can I able to ask you?
definitely, no issues. So you can. I will share my email ID also now in the chat
Okay.
box.
Okay.
You can mail me anytime.
Okay.
Also, any of the TAs is also fine. I have posted my email ID in the comment box. You can mail me anytime.
Yes, sir.
Uh, Also, in the discussion forum, I would also suggest you to post better rather than mailing me. I would suggest you to post in the discussion forum because many people will be having the same doubt.
Okay. Okay.
So that will be accessible by everyone. The thing is like since you pointed out, actually 1,000 above 1,000 students have enrolled in this course, but very few are like accessing.
Yeah.
Yeah, so
Yeah.
it could be useful for anyone. So that's why I would encourage you to post in here, or you
Yeah.
can in the live any of this interactive session you can share your doubts. There is no issue.
Okay. Okay. Thank you very much, sir. I'll let me note down this email ID, sir.
Okay, sure. So anyone else, any other suggestion? Even if you have any suggestion regarding the session we are conducting, like a better way to solve the problems or a better way to
Yeah, for
illustrate.
me, I'm actually basically geotechnical engineering. And I
Okay,
mean to say, my master's is geotechnical engineering.
okay.
Sir, I'm not able to see the 1 minute. Okay. Mm. But for the person who is new to the subject, no, sir, they
Mm-hmm.
may feel difficulty
Yeah,
in.
yeah.
Mm,
So we have framed this slides and this interactive session in such a way that assuming the previous week's
yeah.
videos are followed, but that may not be practical always.
Okay.
That's
Okay.
why before watching this either in YouTube or attending the session, I would suggest you to cover those videos.
Okay, sir.
Otherwise, you will feel this particular gap that you're talking about. So even
Yeah.
though you're attending now, again you can watch this in YouTube.
Yes, sir.
So before that, I would suggest you to go through the particular week. For example, in this week 9, if you haven't seen the videos, whatever I'm saying won't make any sense.
Yeah. Yeah. True.
So yeah, so I would suggest that. So it is a little time consuming because all the videos and these are 1 hour videos, whatever we are doing now.
Yeah.
So it's up to you. We are just solving simple problems so that all the things are covered. Some concept may not be covered in those videos. That numerical part. That's why we are choosing some problems so that
Okay,
everything
sir.
is covered.
Yeah, definitely. But have to score well in my exam. Definitely,
Okay.
I'll come back to you, sir, with many doubts. I hope so.
Sure.
Is it's a link, no, sir? Where I can post the doubts you said, no?
Yeah. Okay. So I will do one thing. So just before I wind up, just I wanted to mention that the next session is on 1st October and
Yes, sir.
my session
Thank
will be on
you.
3rd October. I will do one thing. I will show illust like how to ask a doubt in discussion forum. This is how it looks like all the weeks. I hope you have accessed this before.
Yes, sir.
So
Have gone through this for
ah,
assignments.
okay,
Yeah.
at the top you have this ask a question. Ask a question. Are you able to see the third one?
Third one.
Yeah, announcements about the course and ask a question. So if you click ask a question, you will be
Yeah. Mm.
forwarded towards a Google discussion forum. So this is a
Okay. Okay.
discussion forum. Here you can add a
Okay.
new conversation and write whatever doubt you want. So the
Yes.
idea is it will be directly sent to everyone, so everyone can see what's going on. So the
Okay.
last doubt was in August. That's why I'm encouraging you to uh, go through it.
Sure. Sure. Thank you very much, sir.
Yeah. So I hope
Thanks a
it's
lot.
clear. Please, as you pointed out, please, I would encourage everyone to come up with some suggestions and any doubts, whatever you have. So I guess if there is no much anything else, we can wind up. Thanks for joining again. Let us see you in the next week. Okay. Thank you. Thank you, everyone.
Thank you, sir.